Okay, now that we have defined what it means by speaking of moist air, we want to now continue on our discussion of psychometric applications. So as we model moist air in equilibrium with liquid water, we make the assumption that the dry air and the water vapor that makes up the moist air both behave as independent ideal gases. And up to this point, we've made that assumption. The equilibrium between the liquid phase and the water vapor, so the liquid phase and the gaseous phase of water, is not disturbed by the presence of the air. What that means is if this volume here did not have any air, but just had a portion of liquid water in it, we know that the liquid water and the vapor, the water vapor, would come to an equilibrium. And that equilibrium would be based on the temperature of the water vapor. And so what this assumption means is that same equilibrium between the water vapor and the liquid water exists with or without the dry air also being there. The partial pressure of the water vapor equals the saturation pressure of the water corresponding to the temperature of the mixture. And so that when we have this scenario here, enough liquid water will actually be released out of the liquid phase, turning it into vapor. At the same time, vapor is condensing back to the liquid state, and based on the temperature, the amount of vapor in this mixture here would be at the partial pressure of the vapor, and that will correspond to the saturation pressure associated with that water at the temperature of the mixture. Okay, with that in mind, let's define a couple of other terms. And one of the terms that we want to define is the term referred to as the dew point temperature. And basically, what the dew point temperature is, it is the temperature that if you have a water vapor dry air mixture at a given temperature and pressure, one would assume that one would be at a certain point on the TV diagram for the water. And that point, let's say the initial state of that point would be given here in the superheated region. That would correspond to a partial pressure associated with the water vapor, associated with the amount of vapor with respect to the temperature and pressure of the initial mixture. So at a given temperature of the mixture, we then see that the amount of vapor corresponds to a certain point on the TV diagram. Now before, what we said was that point right there, which is at a vapor pressure 1, if we compared that to the partial pressure at that initial temperature, the ratio of this value to this value is what we call the relative humidity. And when we are away from the dome, the relative humidity is lower than if we were right at the dome. And so we already have talked about the process of going from this point, adding more moisture until we reach the saturation vapor pressure. But for the dew point temperature, we start at this point, and now what we do is we just reduce the temperature, and we don't add or subtract any additional water vapor. And so with reduction in temperature, we see that the partial pressure stays the same, and eventually, as the temperature decreases, it follows this constant pressure line until it reaches the point right here, where at that temperature, that corresponds to the saturation temperature associated with water at that temperature. And so that temperature then would be the dew point for this mixture right here. Now, if we brought the condition to that point, and if we reduce the temperature even more, what would happen is we would then follow an addition. As we drop the temperature more, what happens is some of the water will condense, and it will be at this state here. Some of the water will stay vapor at the saturated condition. And so as we drop the temperature to a final temperature, we'll see that we will then have a mixture that has liquid water condensate at the bottom, and then the remaining mixture would be at the saturated vapor condition. Now, if we were to show that process in a piston cylinder here, where we start off where we have a constant pressure mixture, we start off with dry air and some superheated vapor at this condition right here. If we then take away energy, we cool this and allow the temperature to drop. As we cool it, what's going to happen is the specific volume is going to decrease as we follow this line down, because we're not adding or subtracting any additional vapor. And so we stay at the same vapor pressure for the vapor until we reach point D. Once we reach point D, it's going to occupy a smaller volume. And then all of a sudden, if we continue to lower the temperature, we will then start to see condensate show up, and also the vapor that's remaining in the vapor state is the fully saturated vapor, and it would be at this condition here. So as we then follow this process down to lower and lower temperatures, we will have the mixture itself will be at this condition, and the condensate will be at this condition here. And so it goes along with the statement that we said before, as if we had a liquid water in a volume, the gas phase of this volume will be dry air that is saturated with water vapor. And so the partial pressure of this scenario will be based on the temperature, and again, with liquid water presence, we know that the water vapor is at the saturated state. And so that's showing you how you would get to that particular point. And so the dew point is then basically a thermodynamic property associated with the mixture of moist air at a given temperature and pressure, such that if the pressure drops to that new value, we would then observe that the water would begin to dew out or to condense out, because it's reached the condensation saturation temperature pressure. And so here is a problem that was in the textbook, where one starts with a certain mass of air with vapor. The temperature, the mixture temperature is given. The final temperature is 40 degrees, but at the initial condition, the relative humidity is 70%. And so knowing that that relative humidity is 70%, we start at the 70-degree line. And at the 70-degree line, we know the value of the saturation pressure from the steam tables. So at 70 degrees Fahrenheit, we look up in the table and we see that the saturation pressure is 0.3632 at this point. Since the relative humidity is 70%, this point, the actual initial point then, is 0.7 times this or 2542. And so that gives us the state, the initial state of the vapor. And so again, as we start to drop down, as we start to cool the mixture, as this temperature drops, this value right here will eventually approach the same value in the steam tables. And once we reach this point here, we'll be able to look in the steam tables and we'll see that this partial pressure right here is the saturation pressure for liquid water at 60 degrees. And so that's the dew point. Now in this particular problem, that dew point was 60, and it says that we bring it down even further to 40 degrees. And so as we bring it down to 40 degrees, we then end up with a mixture that has condensate in it, and the condensate will be at this condition, and then the vapor itself will be at this condition here. And at 40 degrees Fahrenheit, the steam tables tell you that the saturation pressure is 0.1217. And so the final state, state 2, would be this particular point for the moist air component, and then any condensate that is there as a liquid would be at 40 degrees Fahrenheit at that particular condition. In this particular problem, just a little bit different problem, what we have is initially we have a constant volume, and it's fixed. We initially have moist air at a given pressure and temperature with a very low relative humidity. And so at that particular temperature, which I'll call T1, we recognize that the initial state is going to be at this point here on the partial pressure line associated with a 10% relative humidity. Now, how do we calculate that value? Well, at this temperature, we use the steam tables to get the P sub G at this point. We then multiply that P sub G by 0.1, and that then gives us the PV1. Okay, now in this particular problem, because the volume remains constant, we then, as we cool the mixture, we are undergoing a constant volume process. And that constant volume process would be on a vertical line straight down because the volume has to remain constant. And so what happens in that particular case is that as we drop temperature, at a constant volume, we'll end up running into the dome at 1 prime. And at 1 prime, that's not called the dew point. The dew point would actually be this point right here. But this point here would be where condensation begins in a constant pressure, or excuse me, a constant volume process. And then what happens is it continues as we cool down to the lower temperature, temperature 2, we will then follow a constant volume process down to this point here. Now, the specific volume can be obtained at this point because it's saturated vapor at a temperature and a pressure, and that's the same volume as at this point, and that's the same volume at this point. Since we know that volume, and we would know what the saturated liquid condition is and the saturated vapor condition is, we could then determine what the quality of the mixture remaining in that constant volume vessel would be. And so in this particular case, they are asking you, to start off with this condition and cool it down to a certain point, and determining conditions associated with that final point. The second example on this sheet here is determining the heat transfer. And so in this particular case, because it's a constant volume process, we would be interested in the internal energy associated with the mixture at this point. Since there's no volume change, there's no boundary work, and we're interested then, once we finally get to this point here, there's an internal energy associated with that particular condition. And again, all based on the specific volume and the total volume. That's how we could come up with the mass. But once we get to this point, the change in the internal energy times the mass is simply equal to the heat transfer. Because again, there's no work and it's all heat transfer from the first law going from state 1 to state 2. In order to evaluate or to determine the humidity ratio of a moist air mixture, there is a technique that can be used, and the technique is shown schematically over here on the left-hand side. And so what we have is we have moist air that comes in to this container, to this flowing system. And what happens is there's a mixture pressure, a mixture temperature, and an unknown value of the humidity ratio. And we're trying to determine what the humidity ratio is. Okay? And so we know coming in here that there's a mass of dry air and a mass of vapor that's coming in. And we also have, as this air comes in, it's like moist air that's in a contained vessel. We recognize that this liquid water is going to absorb some heat, absorb some of the heat from the air and cause some vapor to be emitted or vaporized off of the liquid surface. And what happens is, if this is a long enough time period, what will come out is the dry air will become fully saturated, and it will reach a value of the mass of vapor. Because again, there's enough time and this temperature is such that there's energy in the air, and that energy will come down and allow some of the liquid water to vaporize, and that vaporized water then combines with the incoming water vapor to fully saturate. And so after it's going across here, what's going to happen is the temperature, which came in at a mixture temperature, will actually drop to a lower value of temperature called TAS. And that TAS, the AS, stands for adiabatic saturation. It's an adiabatic system that there's no heat transfer coming in, but what happens is the temperature drops because some of the energy saturates the water or causes the vapor in the water to come and join the vapor that's already there. And so one could measure this adiabatic saturation temperature in this process. One would put a thermometer or some kind of a thermocouple in. Not only have you measured this temperature, but then you measure the lowering in the temperature. You assume that the pressure stays the same, and what has happened is the humidity ratio associated with this mixture here is now this based on this value of m dot v over this value of m dot air. And we know from an equation that we developed earlier that that's simply equal to 0.622 times the vapor pressure at the saturated temperature. And so since we measured the T sub AS, this value right here can then be obtained from the steam tables at that particular temperature. And that is our vapor pressure at the saturated condition. And so once we measure this T sub AS, we then can calculate the omega prime associated with this, and then we can perform what is the first law of thermodynamics to actually determine what the incoming humidity ratio was. And the first law is shown right here, where basically you have the air that is lowering in temperature, so there's some enthalpy there. You have then the the difference between the liquid and the vapor at the saturation temperature. That is the enthalpy required for the evaporation process. This is how much vapor per mass of dry air. And then this term right here is the difference between the enthalpy of the gas coming in, that is the vapor enthalpy, and this is the difference of the enthalpy at the temperature of the adiabatic saturation process. And so this equation here we'll see a little bit further when we go into the first law for a system like this. What's actually happening in this particular case is that we start at this value here as we come in, and we're actually following a process that because water is being added to the mixture, we aren't going down a constant partial pressure line. We're actually adding, and so the partial pressure of the vapor is increasing until we reach this point, which is at this point here. So this is actually the process. So this is the state of the water vapor coming in. This is the state of the water vapor exiting. And so that's actually the adiabatic saturation temperature that one can measure, and then from that and the first law determine what this unknown value of the humidity ratio is coming in. And so with that, this is a device that can do precisely that same thing. This is what is called a slingshottometer, and this is a electronic version. And what happens is on this device here you have two thermometers. One thermometer is wrapped in some gauze that has water in it, and as you sling this around, what happens is the unwrapped bulb, called the dry bulb, measures the local temperature, and the air that flows through and saturates itself then corresponds to the wet bulb temperature. And so the wet bulb temperature and the dry bulb temperature are both obtained, and with a chart which represents this process, you can then figure out the state, the humidity ratio associated with the air in question. And this is a similar device that's electronic in nature, again with the air coming in and the air flowing out. And in this case there might be some type of a mirror that is cooled, and the mirror cools itself until condensation occurs on the mirror. And so electronically cooling and causing condensation to occur on a surface then can give you the same effect as what you do here, causing the wet bulb temperature to decrease as some of the energy comes out of the air to cause the vapor to saturate. Okay, so next time we'll then discuss how all of these thermodynamic properties for a mixture of moist air can be presented on a psychometric chart.